Okay, this is a review for the third midterm. It's in week 13, again, Monday, Wednesday, and Friday. Come all days, of course, as you know. Close book, close notes. Bring a calculator. Equation sheet will be provided. It'll be the equation sheet that is down below this. And the topical material is from conservation of energy in week 8, dimensional analysis in week 9, and pipe flow in weeks 10 and 11, excepting the part on pipe flow networks, which was 11.3. So that's not included. There are 3 questions. They're basically those 3 segments in order. The first one is conservation of energy, which is the Bernoulli equation with head loss and pump heads in it. There's always a Buckingham Pi question and how to use dimensional analysis from week 9. And there's a pipe flow question, which is actually a type 1 question. And also the Monday question is also a pipe flow question, type 1. In other words, velocities are given and you calculate other things around that. So review the notes that you have for this material. We'll go through this very quickly. Energy equation we dealt with in week 8 is just Bernoulli. That's written between an upstream and a downstream portion. We have to do it from upstream to downstream. I have to be careful to do that. If we do that, then the pump head, which is also in units of length, as these other terms are, is positive if it's a pump pushing energy into the system, and it's negative if it's a turbine which is extracting energy. It'll just come out that way in the system. We also have on the right-hand side head losses. Head losses can be either minor or major. Minor are pipe bend losses and valve losses, which are always a loss factor, KL, typically between 0 and 1, multiplied by the velocity head. And major head losses are incrementally small, but additively, since they occur over long lengths of pipe, they're quite large. And it's a function of the length of the pipe divided by its diameter, velocity head, and multiplied by a friction factor. Both KL and F are really Euler numbers in the system. What this equation looks like, of course, if you draw it from upstream to downstream in an open system, is that you have an elevation head, you have a pressure head, and you have a velocity head. If the pipe is of constant diameter, then the velocity upstream and velocity downstream have to be the same amount. So this blue line would be parallel to the green line. And what these additional parameters of pump head and hydraulic losses mean is you go up from this, what would have been our energy grade line here, to define pump head and the losses which are present in the system in bringing it down for this. So a pump putting energy into the system, a turbine taking energy out of the system are shown as this, and this is the head losses due to frictional losses in the system. You can write it between upstream and downstream. You can write it on top of the big tank from upstream and downstream. If that's the case, then the velocity 1 and velocity 2 are 0. And you're left with an elevation head upstream and downstream. I guess this would be 2. And you can solve Bernoulli from that. If you want to write it just for a pipe, you could write it between, as we did in class, between points 3 and 4. In that particular case, the elevations drop out, but you're left with a pressure upstream and downstream, which you have to account for, which is just the distance from this point to the surface of the fluid. And so you can do it either way. The pump head is always defined in terms of power. Uppercase W, I guess we don't want to confuse that with the relative velocity. W dot is just the power, which is in watts, which is in joules per second, which is in Newton meters per second, divided by mass flow rate, which is kilograms per second, and acceleration due to gravity. You can write the mass flow rate in terms of volumetric flow rate times the density, which also is kilograms per second. and we know that volumetric flow rate is just the product of velocity along the pipe multiplied by its cross-sectional area. We define pipes in terms of their diameters, their lengths, as in use on these friction factors and Moody charts. It has a relative roughness, which is given by a height and amplitude of that roughness relative to the diameter. And so we need to be mindful of that. And I guess the other parameters would be a density of the fluid and a viscosity of the fluid, which define our behaviors. If we want to solve for flow in pipes, then we need to use a Moody chart. Moody chart divides the flow into two regimes: a laminar flow for Reynolds numbers less than about 2000, and transitional or turbulent flow above those magnitudes. The Reynolds number is inertial forces to viscous forces, a velocity, a density, and a characteristic dimension, usually the diameter of the pipe or equivalent hydraulic diameter. And the viscous forces are given by the viscosity of the fluid. The threshold value from laminar to turbulent is usually 2000 or 2200. In a laminar regime, the friction factor is a function of an inverse function of Reynolds number, so it varies the Reynolds number. For a circular pipe, it's given by 64 over the Reynolds number. Reynolds number defined here. And for turbulent flow, it's given as a function of relative roughness. So large relative roughnesses would go here, smoother pipes would be down here. And the important things to note are that for laminar flow, the friction factor is a function of Reynolds number, but not relative roughness. And for turbulent flow, the friction factor is a function of relative roughness, low relative roughness, high relative roughness, but it's not a function of Reynolds number. The fact that this curve is horizontal means that it's the same for every Reynolds number. So these curves have different attributes in terms of solving pipe flow problems. In laminar flow, it's a parabolic distribution, and the velocity varies across the segment of the pipe. We convert this into an equivalent uniform flow velocity, and of course that uniform flow velocity is the magnitude that's used in here. And I guess also we know that this is an Euler number, which is a pressure divided by density times average volume, average flow velocity squared. There are two pipe flow questions, question 1 and question 3. So Monday and Friday are both pipe flow elements in them. They're both type 1 questions, which are easiest to solve in the context of a test because you're given a velocity. You can directly calculate a Reynolds number. You directly know what the friction factor is. So you can either calculate what the head losses are or the pump heads are, and then calculate the other points directly without iteration. If you need a Moody chart, you'd be given one either on the equation sheet, which I guess we have here, but actually for question 3 on Friday, you get a Moody chart on your test question to be able to use to solve the equation. The Buckingham Pi question, which is on the Wednesday, always a Buckingham Pi dimensional analysis question. It's just a recipe to be able to calculate what the non-dimensional parameters are, the pi groups. And it's a recipe. You look to see how many, you define your problem in terms of your variables. And I guess in this case, this would be the variables defining the system, which would be in terms of diameter, density, velocity, length, and viscosity, and other parameters that might be in them. You look at your system to see which of mass, length, and time are represented. In this system, length is represented here, mass and length is here, and time is represented here. So all of those variables are represented. And the way that you choose your repeating variables is to have variables that represent all of mass, length, and time in the repeating variables. You can calculate the number of pi groups you have by noting the number of variables, which in this case is 5, and subtracting from that the number of mass, length, and time which are represented, which in this is 3. And so in this particular problem, if this was a problem, then it would be described by 2 pi variables, pi 1 and pi 2. And then there's a formalism to do that. Typically in all the tests that you look at, you'll see that you're given the repeating variables because you get different pi groups if you choose different repeating variables. So these repeating variables include all of the components of mass, length, and time represented in the system. There has be a non-repeating variable, which is length and viscosity, which are the ones that are not included in the repeating variables. And you define the pi groups as the non-repeating variables multiplied by the repeating variables to the power a or b or c. And so the problem then is to be able to figure out the magnitudes of these exponents, a, b, and c, so that this turns out to be the mass, length, and time in the groups are equal to 0, 0, 0. And so we can do that directly from this. You do it for pi group 1 with the variable and the repeating variables to figure out the values of those a, b's, and c's. And then you do it for the second pi variable, substituting this length with the viscosity. You'd end up getting exactly the same variables of a, b, and c here, because you're just repeating it, but you'd end up with a different term for including the viscosity. So you'd end up with 2 pi groups. It would be pi 1 and pi 2. If you only had 2 pi groups, then you'd have a unique curve which links pi 1 and pi 2. Typically pi 1 is the Reynolds number, or of these 2 groups, one is a Reynolds number and one is an Euler number. And so these you could imagine representing the Moody charts, where you choose to do your experiments at the right kinematic similitude, the same Reynolds number between your model and prototype. And if you do that, then this curve would be from doing a whole bunch of experiments using these different values of pi 1 and pi 2, so that when you choose similitude between the Reynolds number of your model and your prototype, you go up to this curve and you go across and you have the Euler number, which is exactly the same between the model and the prototype. That's what we're doing. It's exactly the same as using a Moody chart, right? You choose the right Reynolds number, you find it where it intersects the curve, you take it on here to get the right Euler number, which is equal to a friction factor. This is the Reynolds number, and this is equal to pi 1, and this is equal to pi 2. And you can use that if you're doing your experiment at the right kinematic similitude, you get the right dynamic similitude, and by comparing the behavior for the same Euler number for the prototype and the model, you can find out what the forces or the pressures driving the flow are in the system. So that's Buckingham Pi. I guess this is the recipe for getting the pi variables, pi 1 and pi 2. If you want to apply that, you apply similitude, meaning that your model has the lengths scaled to the prototype in the exact same proportion. If it's a 10th scale model, then every length on the model is a 10th that of the prototype. You want to do your experiments at the same Reynolds number to represent the same flow regimes. And so the Reynolds number of the model and the prototype should be the same. The Reynolds number is always given in terms of density of the fluid, the velocity of the fluid, a characteristic dimension, often the diameter, but it might be other things, and the viscosity of the fluid that's flowing around it. And once you ensure that the flow regime that you're doing your experiment on your model and prototype are both the same, then you can look at dynamic similitude. So you match the Euler numbers for the model and the prototype. The Euler numbers are pressure divided by a density and a velocity squared, again, non-dimensional. And if you know, for instance, the forces applied on your model or the pressures on the model, I guess forces would be equal to, a pressure is equal to a force over an area times rho v squared. So that's another way to write this expression, and that allows you to be able to calculate, say, the force on the prototype from the force that you measure in the wind tunnel on your model. So in other words, you can calculate the lift on a wing on the 777 in real life if you do an experiment in the wind tunnel. We've already said what the pi groups mean. You get a relationship between the two pi groups. If you only have two pi groups, you'd have a single curve. If you had multiple pi groups, then you'd have one for a third pi group. So this might be, well, for the Moody chart, it's epsilon over d, relative roughness, for different values of this relative roughness. And so you have multiple ones of these. And so using this, you can get the behavior prototype. In Buckingham Pi, you're often required to figure out what the units are. If you need to know what the units are, you can always break it down into parameters you know. Pressures, for instance, would be newtons per meter squared. Newtons would be a force, which is equal to a mass times an acceleration, which would be equal to kilograms meters per second squared, or this would be mass, this would be length, and this would be t minus 1. Is that right? Yeah, okay. Mass per length squared, which would be, well, that's not right. So force is, yeah, okay, so that is right. And then this is force, which goes into this, which goes down here, which is equal to kilograms per meter squared times meters times second squared. And so you have a, this is not, so you have a length squared. So this term here becomes to the power of length minus 1. So that's this here. Likewise, if you need to do the same for viscosity, you know that, for example, shear stress is equal to viscosity rate of change of velocity divided by a length. And so by that token, viscosity would be equal to a shear strength over a velocity times a length. And so if you know that shear stress is equal to a force divided by an area multiplied by a length divided by a velocity. Length is length, velocity is length over time. Force, we've just defined that for this here, which you can define, and the area is length squared. So you can always work towards that if you need it. But you might want to remember these just because these would be typically ones that would come up in a Buckingham Pi question, which aren't so easy just to remember, maybe off the top of your head. So density is easy, velocity is easy, viscosity is not so easy, and if pressure was one of these, then you might want to be able to remember exactly what those units are. So these might be two ones that you keep and recall, but I guess also you'd have them here on your equation sheet. Okay? Good luck.